in this video, we are going to look at the basics of vectors. We're not going to get into anything too tricky here. We're just going to start out with what is a review of the physics concepts that we learned about last year. So, what is a vector? Well, a vector is a quantity that has both, sorry, it's taking me forever to write, that has both a direction as well as a magnitude. So basically, a vector tells you how far to go and in what direction are you going to go. And generally, when we think about our vectors, we measure them from the x-axis. So if I were to think about a vector, I have a vector right there. And generally, what we're given is we're given the magnitude of the vector. Let's say this vector has magnitude of 20, and we're given the angle of the vector. I'm going to say this angle is 40. So we would see this written as 20 at 40, or some other combination of those two things. But you're always given that magnitude, which is basically the distance along that line, or the length of that line, and the degree that you have, which is 40. And again, it's measured from the x-axis, typically. One thing that we like to think about with our vectors is, if you look at it, that diagonal line has two parts to it. It has a horizontal part and it has a vertical part. And what these are known as are components. So our vectors generally have an x component and a y component. And sometimes we like to know one of these things or the other or both, so they help us figure out a little bit more about the traveling of whatever it is that's moving along that particular vector. Now, if you look at your x component and your y component and then that original vector that was drawn, you notice that there's a nice little right triangle, which means we might have to review a super cool concept called trig. So we looked at a few things involving trigonometry, or trig, and they all had to stem from the idea of a right angle. So we're going to review what those things are, because we're going to need them to find our components of our vectors. So there are three main functions in trigonometry that we are going to think about. And the first one is cosine. The cosine of an angle can be found by looking at the x part of the triangle over the hypotenuse of the triangle. A lot of the times when we're looking at our triangle, we would call this angle theta, and we would say that this side that is next to angle theta is called the adjacent side. The side that is across from angle theta is called the opposite side. And then that is the hypotenuse. So, back to cosine. The cosine of that angle is found by looking at the x part, the adjacent part, over the hypotenuse part. The sine of that angle is found by looking at the y part, or the opposite, over the hypotenuse. And the tangent of that angle is looking at the opposite over the adjacent. Sort of like looking at slope. We do our change in y's over our change in x. Now, we also sometimes don't know the angle, and so we need to go backwards, and we're going to find the angle. To do that, we need to use inverse trig. It's really very similar to the original ones, except in this case, we're going to say the inverse cosine of the output. You know how when we found inverse, we switched the input and the output. So that means adjacent over hypotenuse will get me angle theta. So if we found the inverse sine, again, we're going to switch the input and the output. We're going to have opposite over hypotenuse equals angle theta. We can also do that with tangent function, which is tangent inverse of opposite over adjacent equals angle theta. Now, if you're using a calculator for this, which I hope you are, I only know a few of them in my head, then we are going to also sometimes see it written as arc, cosine, arc, sine, or arc, tan. Now, for our purposes, the best thing to do is look at these angles in terms of degrees. So before we get started too far, before we get going too far, you want to make sure that you have a calculator that is in degree mode. The Google calculator has the degree mode, so does Desmos. You just need to go into the settings, make sure you're using the right thing. Otherwise, you're going to get kind of nonsense as your answers. So let's utilize that trigonometry that we talked about, and let's find some x and y components of vectors. So let's say we have a vector that is a magnitude of 60 at a heading of 40 degrees. If we think about this as a graph, we would see that our vector is not quite 45 degrees, but 40. So if we use the trig that we just talked about in order to find this, we know that finding the x component is going to be related to the cosine function. So if we were to look at our cosine function, we would know that the cosine of 40 equals the opposite, or the adjacent, sorry. We don't know the adjacent, so that's the x component we're looking for, over the hypotenuse, which in this case is 60. So we're going to multiply both sides by 60. So we're going to have 60 cosine of 40 equals x. Alright, so we're going to utilize our lovely little calculator to do most of the hard work for us. We're going to do 60 cosine of 40, making sure we're in degree mode, and that is going to get us an x component of 45.96. Now let's think about the y component. So the y component is going to be the sine of 40 equals the opposite, which we don't know, the y component, over 60. We're going to end up with 60 times the sine of 40 will get us the y component. And then we're going to go ahead and get our calculator to help us out with that as well. And we are going to end up with a y component of approximately 38.57. So those are the two components of this particular vector. Alright, so let's look at another one. Let's look at a magnitude of 14 at an angle of 90 degrees. So again, I'm going to look at it visually. I like to visualize stuff. 90 degrees would be going up, and it's 14. So we're going to use our functions again. To find the x component, we're going to use cosine. So the cosine of 40 is going to be the x part over the magnitude, which is 14. So we're going to have 14 cosine. I wrote 40. It should be 90. Sorry. Equals x. And then again, we're going to use our handy dandy calculator to do this for us. Although if you are a savvy person, you already know what the cosine of 90 is. And the cosine of 90 is 0. 14 times 0 is 0. And that means that we have an x component of 0. Now look at your graph. That kind of makes sense, right? It's going straight up and down. It doesn't go side to side at all, so it's not going to have an x component. However, it most certainly has a y component. So we're going to find the sine of 90, which is the y component, over the magnitude. Multiply using our algebra. And we'll have 14 times the sine of 90 equals y. And again, if you are savvy, you already know what that thing is. If not, we'll utilize our calculator. And we can get that the y component is 14. Now, I want you guys to notice what I've been doing here in all of these calculations is that I'm always ending up at that step with the magnitude times the trig function. And you can go ahead and skip to that step if you want to, and I'm going to do that in another couple examples for finding x and y components. Alright, so let's look at finding components of a couple of other examples. Let's start out with a magnitude of 5 at a heading of 130 degrees. So if we think about this visually, our 5 is going to go back. That's not quite 180, but more than 90. It's going to be our 130 degree angle. So this is one that we could do a couple of different ways, but I'm going to stick with what we're using before. And I'm going to go straight to the magnitude times the trig function, since we saw that that was going to happen regardless. So to find the x component, I'm going to have 5 times the cosine of 130. So utilizing our calculator, we are going to see that that is negative 3.21. And if we look at our graph, we can kind of see that makes sense. To go negative, the vector is going backwards, and that's in the negative direction on our coordinate plane. And then to find the y component, we're going to do 5 times the sine of 130. And we get a y component of 3.83. And again, if we look at our little sketch of our vector, those numbers make sense. So let's try one more example of finding components. And let's look at a vector that has a magnitude of 12 and a heading of 180 degrees. So again, I'm going to do a sketch first to see what's going on. 180 degrees will be going in that direction. We have a 12. There's our 180. Now, some of you guys might be able to make a connection from that 90-degree example we did, but I'm going to show you that it still works with the trig way as well. So to find the x component, I'm going to do 12 times the cosine of 180. And that is going to get us negative 12. Now, if we look at our picture, yeah, that makes sense. Horizontal, negative 12, because the magnitude was 12. Now, let's do the y component. And again, I bet some of you guys are going, no, why are you doing that? We already know what it's going to be. But let's go ahead and double check with our calculator anyways. So, again, you're going to type in 12 sine of 180. Pause as you type it in. Alright, we get our y component to be 0. Which again, look at your drawing. It doesn't go up or down at all. That vector is only going horizontally, so it makes sense that it only has an x component. So in all of those cases, we were given the angle and we just needed to find the x and y components. So let's say we don't know the heading direction, we don't know the angle, and we are given the components. What can we do to find the other information about the vector? Again, we're just going to rely on some trig. So let's say we have a vector that has an x component of 5 and a y component of 7. Before we get started doing too many calculations, I'm going to think about what that would look like. An x component of 5 and a y component of 7, my resultant vector would kind of look like that. Now, when we did our review of trig, we saw that if we were going to be using the inverse, we were going to be using the inverse functions. So in this case, I could say that the cosine inverse of the x components over the hypotenuse would get me theta. Well, I know the x component, that's easy. Do I know the hypotenuse? No. However, this is awesome. Everything comes together. This is a right triangle, and you know that that one is 5 and that one is 7. Could you find that missing hypotenuse? Yes, you could. We know that a squared plus b squared equals c squared. So we know that 5 squared plus 7 squared equals c squared. So we know that 25 plus 49 equals c squared. So we know that 74 equals c squared. We can take the square root of that, and that will get us the magnitude that we are going to need. So in this case, it is going to be, and I'm going to use decimal for this, it's going to be about 8.60. Well, now we can go back and we can actually utilize that inverse cosine function. We can say that the cosine inverse of the x component, 5, over the hypotenuse, 8.60, is going to get me my theta. You can use your calculator to do this at this point. Remember that some calculators will use arc instead of the -1 symbol. So when I got this, I ended up with an angle theta being 54.45 degrees. And since I drew my picture pretty not too bad, it's pretty clear to see that that angle is more than 45, less than 90. We're pretty close to 54.45 degrees. Now, you could have done this another way as well. You could have used the sine function, or you could have used the tangent function, since I gave you both components. And either of those would have worked as well. It really doesn't matter as long as you are consistent about what you're using. Since I chose to use cosine, I needed to use the x component. If I would have chosen to use sine, I would have needed to use the y component. And if I wanted to use tangent, well, I would just use x and y, and really all of this nonsense that I did here was moot. But I wanted you guys to kind of see some of your options there. I'm not going to do a ton of examples of finding angles because depending on what you're given, each one's slightly different, but they all come back to using those inverse trig functions. So now that we know how to find the components of the vectors, we are going to use this to add vectors together. I'm going to use the triangle method. There's another method out there called the parallelogram method. I like the triangle method because it allows us to use some of the things that we already used in this video regarding right triangles. Now when we're adding vectors, what we're doing is we're finding the sum, which is referred to as the resultant vector. So if you were asked to find the resultant, you would be needing to find the sum. So to start out, we're going to look at an example. Say we have magnitude of 3 at 45 degrees, and we have a magnitude of 5 at 135 degrees. So let's think about this as an image. So we have the 3 at 45 degrees, and we want to add to it the 5 at 135 degrees. To add these together, tip-to-toe method, we want to start our origin again at the end of the first vector. I'm going to add in the second vector, the 5 at 135 degrees. So we're going to see our resultant vector is going to be this guy right there. And that's what we're going to be looking for. We're going to be looking for the resultant vector. And to do this using this particular method, what we're going to need to do is add the x components, and then also add the y components. Then we're going to analyze what this sum is, and we're going to use that to find the magnitude and direction of our resultant vector. So let's use what we learned before about finding the x components. The x component of the first vector can be found by doing 3 times the cosine of 45. And the y component of that vector is 3 times the sine of 45. So we can utilize our calculator to help us do that. And we are going to end up with 2.12 for the first one. And we're also going to get 2.12 for the second one. Now we're going to find both of those for the second vector. So we're going to do 5 times the cosine of 135 degrees. And we're going to do 5 times the sine, I don't know why I keep leaving out the I, of 135 degrees. Again, utilizing our calculator to do this good stuff for us, we are going to end up with negative 3.54 and and then we are going to have 5 sine 135, 3.54. Alright, so now we have to add these things together so that we can find the resultant vector. So if we have 2.12 plus negative 3.54, that should get us the x component of our resultant. And so the x component of our resultant is negative 1.42. If we look at the image that I drew, that kind of makes sense that the x component is negative. I'm going to do the same thing with my y components. I'm going to do 2.12 plus 3.54, and that's going to get me 5.66. And again, we can see in our image that makes sense. Now, if you look at what we have with this resultant, we do have another triangle, and so we're going to have to utilize some triangle things to actually find the magnitude of the resultant vector as well as the angle or the degree that we have going on. So let's start out with the magnitude. If we look at our resultant vector, it ends up being the hypotenuse of a right triangle, with the sides being the x component and the y component. So to find the magnitude, we can utilize the Pythagorean theorem. So our resultant vector, c squared, is going to be equal to negative 1.42 squared plus 5.66 squared. We'll take the square root of that. So what I'm going to do is I'm just going to type all of that into my calculator. You might want to pause and type that into your calculator as well. And I ended up with a magnitude of 5.85 when rounding appropriately. So that gives us our magnitude of the resultant vector. But we also want to find the angle. What is the angle going to be? Well, since I have the x component and the y component, I can go ahead and I can use the tangent function, and I don't have to do any other extra calculations. And in this case, we're going to have to use inverse tangent function to find this. So, because we're trying to find the angle, right? So the inverse tangent function is going to be the y part divided by the x part, and that should get us theta. Again, we're going to utilize our calculator to help us do this. Alright, and I got theta was negative 75.9. Now, I know you're looking at that picture and you're going, wait, what? That doesn't make any sense. If we're going to deal with the x-axis there, our angle is not negative 75.9. But keep in mind what triangle we were using to actually find this. We're using this triangle that's sort of on the other side. So when we found theta, we actually found theta in relation to a different place than you normally measure the vector from. So in this case, we have 180 degrees. We found this little part, and we need to find the difference between the part we found and 180 to actually get our heading. So 180 and then minus 75.9 is going to get us our actual angle. And in this case, our actual angle is going to be 104.1 degrees, again because I was doing some rounding. So our resultant vector has a magnitude of 5.85 at a heading of 104.1 degrees. So let's look at another addition that we have going on here. Say we have the two angles, 8 at 100 and the two vectors, 8 at 330 degrees and 4 at 45 degrees. I'm going to think about this visually because that'll help me. It helped us in the last one. So 8 at 330 degrees, well 330 degrees is going to be all the way around over here. So there's my 8 at 330 degrees. Then if we're going to add in 4 at 45 degrees, I'm going to restart my origin. I'm going to do 4 at 45 degrees. It's going to be a little bit less, but going up that way. So we are going to be looking for our resultant vector, which I'm going to do in blue. To do that, again, we're going to need to find the sum of the components. So for the first vector, the x component is going to be 8 cosine of 330. And the y component, I'm running out of space, is going to be 8 sine at 330. And then for our other vector, we're going to have 4 cosine of 45 degrees. And we're going to have 4 sine of 45 degrees. So we're going to need to utilize our calculator to find these things. So we're going to do 8 cosine of 330, and that is going to get us about 6.6 2.93. And then I'm going to do 8 at sine of 330. And that is going to get me -4. What a nice number. We can do the same thing for the second vector. We're going to do 4 cosine of 45 degrees. And that's going to get us 2.83. And then we're going to do 4 sine at 45 degrees. And that is going to get us another 2.83. Now remember to find the resultant. What we're going to do is we're going to combine these two things together. We're adding vectors in this case. So I'm going to do 2.83 plus 6.93, and that is going to get us 9.76 for our x component, which fits with the picture I drew. Then we're going to have -4 plus 2.83. That is going to get us -1.17, which also fits with the picture I drew. So remember that this is the x component and the y component. And so what we can do is think about this as a right triangle, and we can find the magnitude of the resultant by using the Pythagorean theorem. So we know that 9.76 squared plus -1.17 squared equals c squared. So I'm going to add those together and find the square root. So you might want to do the same using your calculator so you can check me so I don't do anything wrong. Can you hear that? There's construction going on behind my house. Ha ha. Alright, so I got my resultant to be 9.83. And that kind of makes sense. It's bigger than the other two when we were adding them together. Now we also need to go ahead and find the angle that our resultant vector is at. And I'm going to use the tangent function to help me do that. I know that the inverse tangent is going to be the y component over the x component, and that will help me find theta. I know you're going, what is this lull? I'm using my calculator just like you guys should be doing. Alright, so I got theta to be -6.84 degrees. But again, we want to think about what that angle actually refers to and how we can actually use that in the picture that we have drawn. Now, if we look at our picture, we can see that we're actually part of a whole circle. And if we want to do the whole circle all the way around, we're going to have to do 360 in this case and take away our difference from 360. So I got 353.16. So our resultant vector is a magnitude of 9.83 at a heading of 353.16 degrees. Now, what's cool about this is I can continue adding 2 vectors, 3 vectors, 4 vectors, 5 vectors, and so on and so forth. And as long as I use this same method, I'm just going to be utilizing the same functions. It's just I'm going to have to do my initial calculations, my x and y components. I'm going to have to do more of those. I would bore you guys more and more with my doing 5,000 examples on this, but really you might want to check out the physics classroom. We used it a lot last year when we did physics for some examples of vector addition, as well as the parallelogram method if you want to check that out too. So as always, I'm going to end with a little recap of what we talked about for our vector basics. Now keep in mind, this is just basic vector stuff. We remember that a vector has both a direction and a magnitude. And from each vector, we can find x and y components. And to find those x and y components, trig and right triangles are your friends. So we have to remember our trig functions. Scroll back in the video a little bit if you want to review what those were. We're going to use cosine to help us find our x component and sine to help us find our y components. And we can also do vector addition. Remember, with vector addition, we are looking for the resultant. And for our vector addition, all we're doing is adding x and y components and then utilizing some of those trig things to help us find the magnitude and the direction of that resultant vector. And as I said before, the physics classroom is an awesome website to help us find out some more about vectors. Hooray.